Welcome to the Two Beans in a Pod, where we take a complicated stack of research and distill it into the knowledge you need.
Today, we're tackling something that's been gaining a lot of traction online. This theory that solar flares, these massive space weather events, might actually be causing earthquakes here on Earth.
Right, you see it everywhere. But the premise is just, it's incredible. The idea that energy from the sun could be strong enough to destabilize our tectonic plates. So our mission today is to verify it. What does the actual data say?
It really forces us to look at the whole Sun-Earth environment as one big interconnected system. We have to look at solar wind, magnetic fields, all these complex variables, and see if there's a real correlation with movements in the ground.
So we'll look at the evidence for link, but also the official geological stance, which is pretty skeptical.
Very skeptical. It's a fascinating scientific debate.
It is. Get ready for some major cosmic geologic tension. And if you want more deep dives like this that cut through the noise, please go ahead and hit that like button and subscribe to the program. It really helps.
Okay, so where do we start?
I think to really get the scale of energy we're talking about, we have to go back in time. We have to talk about the single most powerful space weather event ever recorded, the Carrington event of 1859.
Ah, yes. That event really does set the benchmark. It was caused by a massive coronal mass ejection, a CME, basically a giant magnetic bubble of solar plasma shot out from the sun.
And it hit Earth fast.
Incredibly fast, over 2,000 kilometers per second.
Our magnetic shield, the atmosphere just wasn't ready. And the eyewitness reports from back then, they sound like something out of a movie. People saw auroras, the northern lights, as far south as South Carolina.
Yeah, there was one report that said the eastern sky appeared of a blood red color.
And another one said the sea reflected it so clearly it looked like the ocean itself had turned to blood.
And that light show, that was really just a side effect of this huge electromagnetic shockwave hitting us. When that CME struck, it basically caused Earth's magnetic field to just dump terawatts of power into the system.
So in 1859, the most advanced tech we had was the telegraph system, the Victorian internet, right?
Exactly.
What happened when that massive surge of energy hit those wires?
The whole system was just overloaded instantly.
Yeah.
Operators reported seeing streams of fire pouring from the circuits. The surge was so powerful that, the platinum contacts and the equipment were in danger of melting.
Wow.
In some stations, the telegraph paper itself just burst into flames.
And there's that amazing story about the operator in Washington, D.C., Frederick Royce.
Oh, yeah. He was severely shocked when fire literally arzatased from his forehead to the telegraph equipment.
And then the Boston operators, they figured out they could unplug their giant batteries and still send messages.
Still send messages to Portland, Maine, using only the current from the aurora flowing through the wires.
Yeah.
The sun was directly powering their communication.
That story is so important because it proves, it's hard evidence of the brute electromagnetic force that can cross millions of miles, get through our magnetosphere, and create real, usable electrical currents right here on the ground.
The energy is absolutely there.
So the central question now is, can that energy, that fast flow of energy, get from the atmosphere down to the fault lines, deep underground? How does space plasma translate into, bedrock moving?
Well, this brings us to the proposed mechanism, and it all centers on something called telluric currents.
Okay.
When a CME hits us and causes a big geomagnetic storm, it generates an electric field. That field influences our atmosphere, and this is the key part, it induces electrical currents right there in the Earth's crust.
So the storm itself creates an electrical current that flows through the ground.
Exactly. And the idea is that these telluric currents could act as the final little push, the trigger for a fault that's already stressed out and close to breaking from, years of tectonic pressure.
But is the current from a solar storm actually strong enough? To trigger movement in solid rock, that feels like the big scientific hurdle.
It is the crucial piece. So studies have measured the density of these telluric currents during geomagnetic storms. They're around 10 to the minus 6 amperes per square meter.
Okay, I'm with you so far.
Now compare that to lab experiments. Scientists can artificially trigger seismicity, little earthquakes, in rock samples. And the current densities they use are between 10 to the minus 7 and 10 to the minus 8.
Wait, so you're saying the currents from a solar storm are actually stronger than what scientists use in a lab to intentionally break rocks?
They're in the same ballpark, yeah.
Yeah.
Often slightly higher. And this is, it's profound. It gives us a plausible physical path where solar energy could create that tiny final kick to a fault that's already on the edge.
That's a compelling mechanism. So if it's real, we should see a pattern in the data, right? big solar events happening just before big earthquakes.
And we do. The correlations are pretty striking. Take the 2001 Gujarat earthquake in India.
Right.
Researchers looked back and saw that the Ka values and the electron flux, they both increased drastically about 36 hours before the quake hit.
Okay, for anyone listening, can you break down what the K-Tate index is?
Sure. The Kpa index is just a global measure of geomagnetic activity, basically how disturbed Earth's magnetic field is. A high Kpa means we're in a strong magnetic storm.
So the magnetic field got really disturbed, and the number of high-energy electrons hitting us went way up a day and a half before the earthquake.
The day and a half, that 36-hour lead time, is what gets researchers so interested in the predictive potential here.
And what about that monster X10 class flare back in 2003? That one was huge.
One of the biggest on record. So on October 29th, 2003, that flare in the CME hit us. Proton and electron flux went through the roof, and the Kpa index hit its maximum value, a 9.
And the earthquake.
A magnitude 6.8 earthquake was recorded off the coast of Honshu, Japan, just 2 days later.
But, two events could just be a coincidence. Has anyone applied really rigorous statistics to this?
Absolutely. The best analysis came after the X9.3 flare on September 6, 2017. They used a method called the bootstrap technique to make sure the results were sound.
And what did they find?
A remarkable correlation. The global number of earthquakes, magnitude 4 or greater, it increased by 68% in the time window, right around that flare.
68%, that's not a small number.
Not at all. And regionally, it was even more pronounced. In Greece, seismicity for quakes magnitude 3 and up, it increased by 120%.
120%.
And some of these studies, they found statistically significant correlations with confidence levels as high as 99.999%.
Okay, 99.9999 is. That's extraordinary confidence in science. It suggests this is not accidental. So why aren't we getting 36-hour earthquake warnings? Why isn't the geological community all over this?
And that right there, that is the core of the conflict. You have this strong statistical correlation. You have a plausible physical mechanism, but, well, traditional geology remains largely unconvinced.
Okay, let's spend some time on their side of it because it's a critical counterargument. What's the standard model that pushes back?
The established model is all about internal forces. It says earthquakes are driven by tectonic plates grinding against each other along fault lines. It's all about massive, slow, continuous stress building up for centuries deep inside the Earth.
And the U.S. Geological Survey, the USGS, they're kind of the gold standard for this. What's their official stance?
Their public stance is firm. The USGS states very clearly that they have never predicted a major earthquake, and they do not know how to. All they do is calculate probability based on known tectonic hazards. It's an internal engine, not external.
So geologists look at the colossal energy needed to fracture rock miles deep, and they just say the push from the sun, even with these telluric currents, it's just insignificant compared to the raw power of plate tectonics.
Precisely. They argue the scales are just too different. And they point to their own analyses that have concluded there's, and I'm quoting here, insignificant solar terrestrial triggering of earthquakes.
So the magnetic field might wiggle a bit before a quake.
Right, but they'd say it's just noise compared to the enormous tectonic strain that's already there.
Yeah. I mean, that makes a certain kind of sense. It's hard to imagine a solar storm literally moving continents.
And there's another challenge with the data itself. It's really hard for these studies to separate a real cluster of triggered events from just the normal background noise of the planet.
The Earth is always shaking somewhere.
Always. So critics argue that if your statistical model isn't perfect, you can make a correlation look much stronger than it actually is.
So the debate really boils down to this. Is the solar event the cause of the quake? Or is it just the tiny final straw that breaks the camel's back, pushing a fault that was already, 99.9% of the way to failure anyway?
I think that's the most productive way to frame it, yeah. A trigger from space versus a loading mechanism from deep inside the Earth. And traditional seismology is all in on the loading mechanism.
Okay. But regardless of whether space weather can cause quakes, the danger it poses to our modern world, our infrastructure, that part is not debated at all.
Not even a little bit. This is fact-based, and it's a threat we are actively preparing for right now. Our vulnerability today is so much greater than it was in 1859.
And the main threat is from these things called geomagnetically induced currents, or GICs.
Right. These are basically DC currents, direct currents that a solar storm generates. And they try to flow through our AC, our alternating current power grid.
And our AC systems are not built to handle DC.
Not at all. A strong GIC can saturate the giant magnetic cores inside our power transformers. They overheat, you get physical damage, and you can stress the whole electrical system to the point of collapse. This isn't theoretical. The entire Quebec grid went down in 1989 because of a solar storm.
And we're seeing power companies actually install hardware to protect against this. What are they doing?
A great example is what the Western Area Power Administration, WAPA, is doing. They installed their first neutral blocking device, or NBD, in a substation in South Dakota.
A neutral blocking device, how does that work?
You can think of it like a very specialized filter. It uses a big capacitor that basically blocks the damaging DC from the GIC, but it lets the normal AC power flow through just fine.
So we're literally building circuit breakers for cosmic energy, and I assume the motivation is the staggering economic cost if a big one hits.
The numbers are just devastating. An extreme blackout, say, one that affects 2/3 of the U.S. population, it could result in a domestic economic loss of $41.5 billion per day.
$41 billion a day.
Plus another $7 billion a day in losses through the international supply chain. And the studies show that more than half of that loss is from outside the actual blackout zone. It shows how dependent the entire world is on our grid staying up.
And it's not just the grid, right?
No. These storms can disrupt the undersea internet cables, the repeaters that boost the signal. You can cripple digital traffic between continents. It can even mess with things like directional drilling for oil and gas, which relies on precise magnetic readings.
This has been a true deep dive. Okay, so let's try to summarize. We've got strong statistical evidence for a correlation, sometimes with that 36-hour warning sign. We have a plausible physical mechanism, these telluric currents. But official geology remains unconvinced, focusing only on internal tectonic stress.
What's so fascinating to me is that the Sun-Earth environment really does seem to be this single, holistic system. We already know solar activity is tied to our atmosphere. You see things like abnormal snowfall when the Ki index is low, or erratic rainfall when solar activity is high.
So our magnetic shield and our atmosphere are directly, observably being tweaked by space weather all the time.
Which just raises this huge question, right? Space weather can so clearly influence our magnetic shield and our atmosphere on a global scale. What other more subtle shifts is it causing in the geosphere, in the crust, that we just haven't figured out how to measure yet? Maybe the future of earthquake science isn't about proving solar storms cause quakes, but in showing they're part of this bigger connected planetary system, where solar energy is this constant subtle modulator of the stress that's already there.
A truly integrated system that needs an integrated science. We will definitely be watching this field closely. If you enjoyed this deep dive, please hit that like button and subscribe for more surprising insights into the world around us.
Thank you for listening to Two Beans in a Pod.